So for a chemical reaction, I'm just going to have a hypothetical one here. Compound A decomposes into compound B plus 2Cs. Now the rate is going to be defined as typically chemists like to measure the progress of a reaction rate in terms of a change in concentration. That tells us, how much stuff has gone away or has come in. Now remember that these square brackets equals molar concentration which has units of moles per liter. And we use those square brackets because it's convenient. So we could, if we were so inclined, define the rate of that reaction as the final concentration of B minus its initial concentration over the time elapsed that you studied that. So we would clean this expression up a little more. We could say it's just delta concentration of B over delta T. Now, it turns out, for one reason or another, that the concentration of one component in the reaction might be easier, much more convenient to study than others. So what I want you to think about here is, what would it look like if we were studying the concentration of A instead? Knowing that we want to define a positive reaction rate as a case where reactants are being consumed and products are being made. So what would the relationship between the change in concentration of component A and the concentration of component B be in this case? And what would we get? So think about it. So the idea is that they are not the same. They're related, but they're not the same. And that's because B is a product, A is a reactant. And so the change in concentration would be equal to the of A would be the opposite of the change in concentration of B. One goes up, one goes down. And again, so let's think about that. And why is that negative sign there? Well, remember that we wanted the rate to be positive when reactants are being consumed and products are being made. But so the concentration of A would simply be the delta concentration of A is simply the final concentration of A minus its initial concentration. But so when a reaction goes, the concentration of the reactants are going to go down, which means this is going to be a negative quantity. It's going to be less than 0. And so we put the negative sign in the reaction rate, and that fixes that all up. So now we've talked about if we needed to study the reaction in terms of the concentration of A and in terms of the concentration of B, and how that negative sign would allow us to get the same answer either way. So it leaves our friend C here. So the next thing I want to think about is, well, how would you, and the idea is that we would want to have the same rate, the same reaction rate, regardless of what component we're using, whether it be A, B, or C in this case. So let's switch from this hypothetical reaction, and I want us to think of one more issue here. So let's think of this hypothetical reaction and switch to a real reaction. So here we've got dinitrogen tetroxide, N2O4, and that decomposes into oxygen and 2 nitric oxides. Now I've got two curves on this graph here. So this is an amount, but you can think of this as a concentration as well, as a function of time, going from the time 0 to 60 minutes. So the first thing I want to ask you is the identity of which of these curves corresponds to which reaction component. One of them should be very easy to figure out, and the other one might require some more thought. So think about it. All right, so A is the one that doesn't require any thought because this reaction, like our hypothetical one, has one and only one reactant. And reactants, when we're studying this, reactants start at a high concentration and then go down as the reaction occurs. So unambiguously, curve A belongs to shows you how the amount of N2O4 is changing as this reaction progresses. So the question is, which one is B? Now you've got two choices. Now B is clearly a product because it's starting at 0 and the amount, and by extension the concentration, is going up as time progresses. And so which one is it? Well, math will usually tell you. So if you think about it, let's look at the numbers here. So after 10 minutes, the amount of N2O4 has gone from 1 mole to 0.74 moles, or a drop of about 0.26 moles, right? Negative 0.26 moles. And if you'll look at our curve B here, it starts at 0, and 10 minutes later there is 0.26 moles. So that change has been a positive 0.26 moles. So this grew by the same exact amount that this one dropped. So that's the big hint. So which one is it, and how can you tell? So the answer is in the coefficients. That they seem to be reacting in a 1-to-1 ratio. For every mole of N2O4 that we lose, we'll gain 1 mole of O2. And that is the clue that you need to tell you that that second curve, B, is actually the amount of O2. Now, what about NO? Would you expect it to grow faster or slower than the amount of O2? So would you expect the NO curve to either look like this one or this one? So the lower one or the higher one? Think about it. And the answer is, ooh, I almost got that perfect. The higher one. Why is that? So that's what NO looks like. And simply because, based on the reaction stoichiometry, as N2O4 disappears, O2 is going to appear at exactly the same rate. But because of stoichiometry, NO is going to appear twice as fast, because for every N2O4 that decomposes, you get, for every mole of N2O4 that decomposes, there is 2 moles of NO that are made. All right. And this brings into account the last thing I wanted to show you about as far as expressing reaction rates in terms of concentration changes, is that the stoichiometry needs to be accounted for, because clearly if you measure the rate of change of the NO versus the N2O versus the O2, you're going to get two very different answers. And again, the idea is that we really want we want to get the same answer at the same rate, regardless of which component we pick to express it. So here is a lot of information on a slide, but this is how we do it. Let's take this point by point here. So this is our reaction again. So we learned before that the reaction rates, whether you're talking about a reactant like the N2O4 or a product like the O2, there needs to be a sign change. And if you are talking about the change in concentration of a reactant, you need to put a negative sign in front of it to make sure that you get a positive rate, even though this change in concentration is actually negative. Now, the other factor we need to take into account is that the stoichiometry for reactions will make things come and go at different rates. We already determined that the NO was going to come in twice as fast as the O2. So what do? Well, we divide the delta NO delta dt by 2, and 2 is the coefficient. And that's just a general thing. So whenever you're describing the rate of any reaction, so little a plus little b giving you little cc and little dt, say that fast a couple times, the full form of the rate is going to be equal to 1 over the coefficient times the change in concentration divided by the change in time. And furthermore, if your component is a reactant, you need to put a negative sign in front of there. If it's a product, you still need to divide by the coefficient, but there's no negative sign. And when we do that, it actually doesn't matter which concentration you're studying, A, B, C, or D. You will always get the same reaction rate. And next time we're going to talk about the things that on a molecular scale affects these reaction rates. See you then.